So this are the notes for piecewise functions. It says we're going to take our pieces of the graph, we're going to finally put them on the graph, and we're going to use like the transformations, the parent function tables to figure out how to do this. Okay, so the first thing it wants to do is to graph each piece. So use your knowledge of parent functions and transformations. Then you're going to use your domain restrictions to determine whether the endpoints are going to be open or closed circles. And that's going to depend on your inequality. Like if you look at the first linear function, it has 0 is less than, which means there's no equal bar, so it's an open circle. X, which is less than or equal to, and the equal to makes it a closed circle at 4. And then after we finish graphing it, we're going to erase what is not necessary to make our function match the domain restriction. Okay, so the first function here is a linear line. And the reason I know this is because negative x minus 4 is a linear function. X to the first power is linear. All right, now for linear lines, I'm just gonna make the graph based on my knowledge of how to graph lines. So here it says my y-intercept is at negative 4. And then my slope is negative 1 over positive 1, so that's down 1, right 1. So I'm making my dots. And now I'm gonna go up 1, left 1. All right, now from here, I'm going to go to my restrictions. So 0 is less than x. So if you think about that activity we did the other day, I'm going to restrict it from the left side, and it has to start at 0. So all the dots that are before 0, I'm going to get rid of it. And at 0, we have an open circle. So at 0, negative 4, I'm going to change that to an open circle. And now from the right side, it says it can't go past 4. So every dot that's past 4, I'm going to erase. And this one has an equal sign, so we're going to make this a closed circle, and we're going to exaggerate so we know it's closed. Now when I connect the dots, this is the segment of my linear function that we're looking for the piecewise function. All right, now for the next one, I'm actually going to make a table. So what I'm going to first do is I'm going to identify my parent function. So this one is the square root. How do I know it's not a cube root? It's because there's no 3 inside the thing. All right, so for this one here, let's see if I can fit it on here. So first we're going to start with the parent function of the square root function. So the square root of x. Now, you might recall this previously, we were making these tables. So a square root, the smallest perfect square that would work is 0. You can't use negative numbers because the square root of a negative number does not exist. And then we can use another perfect square of 1, 4, 9. And if you need to go, you can go into 16, 25, and so on. Now we're going to take the square root of each number. So the square root of 0 is 0. The square root of 1 is 1. The square root of 4 is 2. And the square root of 9 is 3. All right, from here, now we're going to look at our function, and we're going to write the transformation. So here's my XY table for my transformations. And the only transformation I see is insiders lie, right 4. In terms of vertical transformations, there is none. So I'm going to write the word none. Now, I'm going to make my XY rule because I'm going to use the XY rule to make my transformed function. So right 4 is x plus 4. And if nothing happens to y stays the way it is. So now I'm going to make my transform table. And I'm not going to show the work here. So hopefully you're just paying attention so you see what I'm doing. So the rule for x is to add 4. So from 0, 1, 4, 9, I'm going to add 4 to each one. So 0 plus 4 is 4, 1 plus 4 is 5, 4 plus 4 is 8, and 9 plus 4 is 13. For my y values, they do not change, so that 0, 1, 2, 3 stays the same. Okay? Now, when I look at my domain restriction, this is perfect because it says x is greater than 4, so in that case, starting at 4 for this is perfect. So now, notice there's no equal bar. So it's going to be an open circle. So you can draw an open circle. You can write the word open. I'm just putting an open circle there. Open actually probably helps a little bit more. The only reason why is because you don't want to confuse it with like it's a 0. So this is open. So at 4, 0, we're going to draw an open circle. And then at 5, 1, they're back to normal closed circles. 8, 2. And by the time we get there, 13, 3 is off the graph. So I'm going to connect these two dots and kind of estimate where it goes. And there is my piecewise function. All right, now it wants me to find the domain and range based off what I've done. So for the domain, we start from the furthest left. There's an open circle at 0. And it continues to this closed circle right here at 4. And that closed circle cancels out that open circle above it. And then it goes to infinity. So you can either do this in set builder or interval notation or inequality. So if I was going to do interval notation, I would say it starts at 0, parentheses, and it goes to infinity. If you think about the way you saw it in delta math, it was an inequality. So we would say x is greater than 0. Now for our range, we're going to go bottom to top. So the bottom part is a closed circle at -8. And as you continue along the path, it has an open circle at -4. Then there's a break between the graphs, right? There's no way to connect them or something cancels out to help me connect them. It's not possible. So the next piece starts at 0 and it goes to infinity. So again, if I was using interval notation, it would start from -8, comma, -4. -8 is a closed circle, that would be a bracket. -4 is a parentheses. Union, and then we start back up at 0, and that's an open circle, and it goes to infinity, which is a parentheses. Now, if I were to use inequality notation, the first piece is a segment, so I have 2 endpoints. -8 is less than or equal to y, which is less than -4. Or, and then we could say y is greater than 0. Okay, so those would be the 2 possible ways I could write it. All right, let's continue on to the next one now. So the next one right here, you see we have a quadratic function and we have an absolute value function. And so let's start with the parent function table here. Now, one thing I'd like to point out here is, so with the square root, if you look at the parent function table, 0 is the smallest amount I can use. That's the smallest number I can use. With the quadratic function, if you recall when we were making tables, I used -2, -1, 0, 1, 2. So I'm going to use those points. But one thing you have to keep in mind, though, is that it is possible that you may have to use more values. So I'm going to go and start with green on this one. And really quickly, how did I know this is a quadratic function? And the reason I know it's a quadratic function is because it has x squared. So it's a quadratic function. All right. So for here, we're going to do xy for our parent function table. I'm going to leave a space because I don't really know if -2, -1, 0, 1, 2 is going to work. But I'm going to see if it does. Okay. So I'm going to square each one of these numbers. So -2 squared is 4. Now I'm plugging it into its parent function, which is x squared. -1 squared is 1, 0 squared is 0, 1 squared is 1, and 2 squared is 4. All right, from here I'm going to write down my transformations. And then I'm going to make my rule. Okay, so insiders lie, we have x minus 1, which is right 1. And then we have y minus 5, which is down 5. All right, for my xy rule, right 1 is x plus 1. And down 5, I think I said that earlier, was y minus 5. Okay, now what I'm going to do next is I'm going to make the table here. But now one thing I want to point out is the restriction is from -2 to 4. So we're going to see if this encompasses that. If not, I'm going to have to go back to the parent function and add more values. Okay, and it won't be that many. It could be 1 or 2 at most, possibly 3, but it's usually 1 or 2 extra you have to add. Okay, so let's go ahead and write our new table here. All right, so to the x values right here, I'm going to add 1 to each x value. So -2 plus 1 is -1. -1 plus 1 is 0. 0 plus 1 is 1. 1 plus 1 is 2. And 2 plus 1 is 3. Now, before I go any further, what I want to point out is my new graph, my transform, has to be between -2 and +4. And right now, I'm looking at my x values. It starts at -1 and it stops at 3. So I actually have to add values. So instead of starting over here at -2, we're going to put -3. And if I asked you what -3 squared was, hopefully you would reply that it is 9. Then on the bottom, we stopped at 2 for x, but we're going to have to go to 3 to see if we can get to that 4 once we transform it. And 3 squared is 9. Okay, now we're still going to apply that transformation, right 1 of x plus 1. So if I took -3 and I added 1, that would be -2. And if I took the bottom one, positive 3, and I added 1, that would be 4. And now you'll see that it said to start at negative 2 and stop at 4, and this starts at negative 2 and stops at 4. Okay, so now we know that we're within our restriction. So for our y values now, 9, 4, 1, 0, 1, 4, 9, it tells the rule says y minus 5. So 9 minus 5 is 4. 4 minus 5 is negative 1. 1 minus 5 is negative 4. 0 minus 5 is negative 5. 1 minus 5 is negative 4. And 4 minus 5 is negative 1. And 9 minus 5 is 4. All right. So that is my transformed one. Again, we're going to go back and refer to the inequality signs to prove whether it is open or closed. So for negative 2, we have no equal bar, so this is open. And on the bottom for 4 for x, it is an equal bar, so this should be closed. Again, if you want to draw an open or closed circle so you know, that's fine. So at negative 2, 4, I'm going to go negative 2, 4. That's going to be an open circle there. Then I'm going to plot the rest. Negative 1, 0, negative 4, 1, negative 5, 2, negative 4, 3, negative 1, and 4, 4, and 4, 4 has a closed circle. And we connect our dots, and we can see the quadratic parabola is starting to take shape. All right. Now we'll go to the absolute value next. And again, just like I did the other one, I'm going to verify that it does work. So let's go ahead and do this in red. So the absolute value, if you recall, let's see if I can fit in here, is negative 2, negative 1, 0, 1, 2. So let's see. So here's the absolute value of x. So it's xy. So negative 2, negative 1, 0, 1, and 2. So oops. Notice I'm leaving a little bit of space on the top, and I'm trying to leave some space on the bottom just in case. So absolute value is the distance from 0. So it makes every number appear to be positive, right? So if I took negative 2 and then I took the absolute value of negative 2, it would become positive 2. Then negative 1, the absolute value of negative 1 is 1. The absolute value of 0 is 0. The absolute value of 1 is 1. And then the absolute value of 2 is 2. Okay. Now we're going to look at our transformations. So insiders lie, we have x minus 5, which is going to be right 5. And then we have a plus 5 on the outside, which is up 5. So my rule would be x plus 5 and also y plus 5. So now we're going to transform these. And again, we're going to verify that our x, right here our restriction says x is greater than 4. So our first number has to be 4. If it's not, we need to go back and add numbers until we get our first x value to be 4. Okay, so the rule says add 5 to each x value. So negative 2 plus 5 is 3. Negative 1 plus 5 is 4. 0 plus 5 is 5. 1 plus 5 is 6. And 2 plus 5 is 7. Now, again, what I notice is I'm supposed to start at 4. And it's a good thing. It actually does, right? If you see the 3, I'm going to do the 3. I'm going to finish with the y's, but I need to start right here. This is where I have to start. This 4 right here. Okay, so let's continue. So y plus 5. So 2 plus 5. We're using the y column now. 2 plus 5 is 7. 1 plus 5 is 6. 0 plus 5 is 5. 1 plus 5 is 6. And 2 plus 5 is 7. Now, when I'm making my table, or sorry, my graph, I'm using these values here. Because my first x value needs to start at 4, not 3. All right, and over here, it says x is greater than 4. That's open. There is no equal bar, so it's not closed. So my first point should be at 4, 6, and that's going to be an open circle. And then we have 5, 5. Then we have 6, 6. And then we have 7, 7. And those points should be enough for you to see my V-shaped graph taking place. And there you go. If you need to add more values, you are more than welcome to. That first circle I drew was kind of big, so let me kind of shrink that up a little bit. So open circle right here. And there we go. Okay, from here, we're going to do our domain and range. And I'm going to do these only in inequality notation. So for my domain, we have started at an open circle at negative 2. And then it continues all the way until we get to this closed circle here. And that closed circle is going to cancel out that open circle. And then it goes to infinity. So this tells me x is greater than negative 2. How do I know it's not equal to it? Because there's no closed circle that will cancel out that open circle when we start. All right, for my range, we're going to go bottom to top. So at the very bottom, we have a curved line, which means it's a closed circle at -5. And if you continue on, we have a closed circle and open circle. The closed circle cancels out the open. But then we have a space between these two, right? So they both go to 4. Closed circle cancels the open circle. But then we have a space between 4, the green, into the green, and the start of the red. So here we have a closed circle, and that starts at 5. And then it goes towards infinity. Okay? So when I write my inequality notation for this one, it's going to be first one's a segment. -5 is less than or equal to y, which is less than or equal to 4, because again, they have closed circles, which means they are included, which means equal bar. Now we use the word or when we're doing inequality, and u when we're doing interval. Or here we can say x is greater than or equal to 5. Okay, and that's how I got the domain and range. Let's go ahead and keep moving on. All right, this next part here says, write your equation for each piece from left to right. Use your knowledge of parent functions and transformations. Give the domain restrictions. Okay, so the first one is linear. Okay, so this right here is linear. This second one here, hopefully you said it's constant because it's just a horizontal line. And this last one, we can see that little V shape that's going to be absolute value. Okay. So for the first one, we talked about it. If it's a line, I did it a little bit differently. Here, I'm going to identify a couple of things. So for the linear line, I have a y-intercept at +3. And then for my slope, actually, let's change this color here. Okay, let's make this blue. So we said our y-intercept is at 3. And our slope, let's pick this point and this point. We go up 2 and right 3, so 2/3. So this right here, how it says f of x equals, that stands for y equals. So you're only putting the equation. So my slope is 2/3 x, and then that's a +3, so +3. Comma, then you have to write your restriction, right? Because this one right here, this has an arrowhead, and that arrowhead goes towards -infinity, and it stops at +3, and 3 is not included. How do I know that for this domain restriction of just this one piece? It has an open circle. So 2/3 x plus 3, and the restriction is if x is less than 3. Okay? Because it stops at 3 on the x value. All right, for my second one, it's a constant. And when you look at it, constant, what value does it hit on the y-axis? It hits the value of 3, right? So it's just the number 3. That's it, nothing else. And then my inequality notation, it's a segment. It starts at 3 and it stops at 5. So 3 is less than x, which is less than 5. But here, our 3 had an equal bar because it's a closed circle. Okay, so those are my domain restrictions for each function so far. Now for the absolute value here, you do have to recall your transformations. So here, my transformations. So we know the original dot, this dot here, is supposed to be at the origin. So we know it went right 5. And then it went up 2. But then it's facing down, so that's a reflection across the x-axis. Okay. So when I put this together, the absolute value looks like this. So reflection across the x-axis comes first. There's no vertical stretch or compression. There's no horizontal stretch or compression. We have a right 5, so that's going to be x minus 5, absolute bar, and then up 2 is plus 2. If, and again, here we can see this is a segment. It starts at 3, less than or equal to x, less than or equal to, and it stops at 10. And that is my domain restriction for the absolute value. Okay, this is a -5, not a -5, just in case. All right, and there is our piecewise function written from that. All right, to evaluate the piecewise function, it says to evaluate a piecewise function for a given value of x, find the interval that x belongs to, then find the corresponding rule of the function for that interval, substitute your x value, or find the corresponding ordered pair on the graph. Okay, so now you'll notice these two pictures are the same. And I've written rules, right? I've written the equations with the restrictions. Okay, so this one right here says use the piecewise function and evaluate it. Okay, so let me kind of show you how to do this. So we've done this before. G of negative 3, let me just refresh you. We have f of x is equal to y. So whatever's in the parentheses is x, and I'm asking you to find y. So it's an ordered pair x, y, but we're really just looking for that y value right there. Okay, so the first one says, if x is negative 3, so we go to x is negative 3, what is the y value? Well, if I go here, the y value here is at positive 1. All right, for g of 5, so if we go to 5, and then we go up, it hits right here, the y value is 1. Okay, now g of 12. Now, if you look at g of 12, the graph actually stops at 10. That's a closed circle right there. That means it does not go to infinity. It stops there. And since x equals 12 doesn't exist, we're going to say does not exist, or you're going to draw the empty set, so a circle with a little diagonal line through it. Now, one thing I want to kind of point out is, notice I used the graph to get these values, but you can actually use the equations, right? If you use those three equations we came up with at the top, like g of negative 3. So what we could have done is we could have said, okay, negative 3 in terms of restrictions is right here. X is less than 3. So then if I plug that negative 3 into there, 2/3 times negative 3 plus 3, it should simplify to give us 1. Okay, so that's just an FYI, and we'll prove it right now when we work it out. So right here, this one says to give the domain. So now we're not given a graph, we're given a function, and we're going to evaluate it based on which domain restriction it falls into. All right, so the first one says g of negative 3. So if x is negative 3, then it falls in the restriction right here that negative 3 is less than or equal to 0. So that means we're going to use this first equation right here. So we do the absolute value of negative 3 plus 5, which is the absolute value of 2, which is 2. Okay. Now for the next one, we see which restriction it falls into. So g of 4, it falls in right here. X is less than or equal to 4. So now we're going to plug in the 4 into the function. So negative parentheses 4 plus 3. And then we can simplify it. Negative times 4 is negative 4 plus 3, and negative 4 plus 3 is negative 1. And last we have g of 0. So now be careful here because there's two zeros. Hopefully you figure out which one correctly it goes into. It goes into the first one because the first one says x is less than or equal to 0. So therefore we take 0, we plug it into the absolute value of x plus 5. So the absolute value of 0 plus 5, which is the absolute value of 5, which my final answer is 5. All right, and that's how you evaluate a piecewise function, either through a graph or through points. The graph, obviously, we go to x, we see if it hits the graph and what's the y value. For the equations, we look at our x value given and we make sure that it falls in the correct restriction. And other than that, that completes the notes for piecewise functions.